Hello everyone. In this video, we're going to see the reductive or non-oxidative reactions of the pentose phosphate pathway. So here we're going to play really again, we have no redox reactions, no NADPH is produced or consumed. And we're going to play again the sugar interconversion game, very similar to what we did in the Calvin cycle. Just reviewing again what is a sugar, a monosaccharide here, which is the simplest sugar. In these compounds, one carbon is always a carbonyl. So every carbon has an oxygen, one of which is a carbonyl, and all the others are hydroxy carbons. Okay, they're hydroxyl groups. How big are they? They can be, up to 7. Usually they're stable in the cell. If you have 8 or higher, they're very unstable. 3 is the minimum. So anywhere between 3 and 7 in real life situations in cells. So what we are about to see really was proposed from in 2 papers, one of which is shown here in case you want to read more. And the idea is the reactions you're about to see, are they the absolute minimum required to get you to the desired output? And hopefully it will convince you that yes, they are. I mean, the economy of metabolism of metabolic reactions has led to this set of reactions. It can get lower than this, the number of metabolic reactions. Well, as it turns out, there you don't need too many enzymes. So let's review again. We have seen transketolase. Transketolase always moves 2 carbon units, and the donor is always a keto sugar, and the acceptor is an aldo sugar. And what you get is whatever was keto became aldo, minus, of course, the 2 carbons, and whatever was aldo became keto, plus, of course, the 2 carbons. It does have a requirement of the donor that you're going to see again. The C3 carbon has to be in the S configuration. And of course, transketolases are TPP dependent enzymes, as we'll see again. Just to review, what is the RS again? It's part of organic chemistry 101. You arrange the groups in terms of priority around the 4 substitutions of the carbon, and depending on whether they go clockwise or counterclockwise, you have the R or S configuration respectively. Transaldolase, it's the enzyme that you use to move 3 carbons at a time. We've seen a special case of transaldolase, just aldolase, okay, which moves the 3 carbons of DAP, dihydroxyisinophosphate. So the donor and the transfer group is DAP. But there is a more general group of enzymes called transaldolases, which works in the same way. It takes 3 carbons from anything, as long as it's, of course, bigger than 3 carbons, and moves it as a DAP, that 3 carbon unit. The donor, again, just like transketolases, is a keto sugar. It has to be, of course, phosphorylated at the last carbon, and the C3 has to be in the S configuration, just like transketolases. So the donor requirements are really the same between transketolase and transaldolase, but what gets transferred is different. The transfer group is just 2 carbons in transketolase, 3 carbons in transaldolase. And both enzymes put that onto an acceptor, which is always an aldo sugar, an aldose. So the carbonyl at the very end. All right. Aldolase, as I said, is a special case of transaldolase. Just the donor and the transfer group is actually DAP itself. The epimerase enzyme. So far we have only 1, 2, 3. That's the 4th enzyme, epimerase, and we're going to have one more, and I think that's it. Which changes the configuration of between R and S of any carbon, okay, without affecting the configuration of any other carbon. And the last enzyme we need is an isomerase, we have seen many times already. It switches the keto to aldo, okay, and vice versa. All right, so what we start with in the pentose phosphate pathway is ribulose 5-phosphate. That's a 5 carbon sugar, and the goal is to take it to a 6 carbon sugar. And this group here from Israel, they put together these rules, as I told you, and they figured out that actually this is the most economical way to get you to the 6 carbons, which is pretty much what the cell uses as well. So there is no other better way to do it, right? And TK stands, of course, for transketolase, TA for transaldolase. And if you play the game right, then you get to the target, which is again the 6 carbons. All right, so this is what we get, ribulose 5-phosphate from the oxidative part of the pentose phosphate pathway. Just to remind you that this is what was left out of glucose, one molecule of glucose, a peroxidized, decarboxylated, and this is what we have. Okay, the isomerase can take it, of course, we can convert the keto form to the aldo form. That's ribose 5-phosphate. That's actually super valuable 5-carbon unit. It can go straight into nucleic acids and some amino acids too. So this is a very, very important building block for biosynthesis, just from a single isomerase reaction. So you could actually see how the pentose phosphate pathway already provides key building blocks for biosynthesis. We've already seen how it can generate NDPH, right, in the oxidative part of the pentose phosphate pathway. But here we're going to try to convert them into something that can be used in glycolysis. That's the whole idea. So the epimerase will take ribulose 5-phosphate, which happens to be in the R configuration. So it's not going to be a substrate for transketolase or transaldolase. So it has to be converted to the S configuration. That's where we bring in epimerase. So we make it now to xylulose 5-phosphate. And then we have 2 5-carbon units, all right? So what's going to happen is we're going to take 2 from one and move it to the other. 2 from the keto, we're going to be added to the aldo. Then we're going to have a 7-carbon unit that's going to be in the keto configuration, and whatever was 5 now will be converted to a 3 aldo sugar. The only thing to remind you from this point here is that transketolase uses TPP, which again serves as an electron sink. We have seen this several times already. Again, this is the reaction we have done on the board and so on and so forth. It's exactly the same thing. And why do we need TPP again as an electron sink? To stabilize the carbanion that is forming, okay, in the reaction. All right, so if we use transketolase with the ribose and 5-phosphate and xylulose 5-phosphate, so this is going to be the donor, xylulose 5-phosphate, that's the keto. It fits all the rules. They're all satisfied. It's phosphorylated, the last carbon, the 3rd carbon. C3 is in the S configuration. So 2 carbons from here will leave and will be added to the aldo sugar, which is the ribose 5-phosphate, and will generate a 7-carbon unit, which we have already seen also in the Calvin cycle. So ceroheptulose 7-phosphate is formed. Okay, that's a keto sugar. And the 2 carbons that were lost from cellulose 5-phosphate, that will leave this compound now into becoming a glyceraldehyde 3-phosphate. That's already a glycolytic intermediate, right? And again, the keto was now converted to the aldo sugar. Now we're going to use Transaldolase. So the idea is that we are really close to 6. If we can add 3 more to the 3, we can make a 6-carbon unit. And what moves 3 carbon units? It's of course Transaldolase. So let's do this. We've seen the requirements before. So this is how it's going to work. The 2 of them recombine again via Transaldolase. So it's already in the right configuration. Okay, the C3 is in the S configuration of, that is the C3 of the ceroheptulose to act as a donor. Okay, the last carbon is phosphorylated. These 3 carbons will leave, will join with a glyceraldehyde 3-phosphate, and now you got fructose 6-phosphate, which is of course a glycolytic intermediate. But that leaves us with erythrose 4-phosphate. Okay, that's a 4-carbon unit. And you can see where I'm going with this, because we have 4. How we're going to go to 6? Then we can invoke again transketolase, and 4 plus 2 will give us a 6. All right, but this is anyway, the reaction leads to a 6-carbon unit that's a glycolytic intermediate, and you can actually even include glyceraldehyde 3-phosphate, and we have glycolytic intermediates. But what we're left with, so from 2 5-carbon units originally, we have now we have generated glycolytic intermediates, and we're left with erythrose 4-phosphate, which is not a glycolytic intermediate. So we go back to the 5-carbon unit, and we combine erythrose 4-phosphate with xylulose 5-phosphate. And as I said, you go from 4 to 2 to 6 by adding 2. Okay, so transketolase will come in. Okay, take xylulose 5-phosphate, and convert erythro's 4-phosphate to fructose 6-phosphate from aldo to keto, as you will see here in a minute. And the xylulose 5-phosphate now is converted to glyceraldehyde 3-phosphate, which of course is a glycolytic intermediate, and we are done. That's it. So we go transketolase, transaldolase, transketolase, and we're finished. And of course, at the beginning, we had to use isomerase and epimerase to make sure everything was in the right configurations for acting as donors. So, and that's the whole scheme that we've seen. Now, if you prefer the actual, so this was our color coding scheme. Again, nothing changed in terms of redox reaction. So this is why it's called the reductive part of the pentose phosphate pathway. We didn't have any oxidations. And if you prefer the, to write out the formulas, here they are. All right. Again, there is no faster, more economical way to get to it with a minimal number of reactions. So this is the absolute minimum number of reactions you need to get you to what you want. Okay, the glycolytic intermediates, which are here, 3 and 6 carbon units. All right, so the overall reductive branch, then we can write it up like this: from 3 pentoses, we got 2 fructose 6-phosphate, so 2 times 6, that's 12, plus 3, which is glyceraldehyde 3-phosphate, equals the number of carbons that came in as 3 5-carbon units. Why? How important is the pentose phosphate pathway? Extremely important, especially in proliferating cells where you need to do a lot of biosynthesis. And how is that the case? Well, we've seen some direct substrates, and really downstream, immediate downstream substrates of the, or products, sorry, not substrate, products of the pentose phosphate pathway, such as NADPH, which is used for reducing power to make a lot of stuff, and actually all of biosynthesis, but especially if you make lipids, as we will see in a few videos down the road, that's a major consumption of reducing power. Ribonucleotides, well, ribose 5-phosphate is, as I said, a very crucial and expensive building block, and cells use it to make RNA and DNA, right? It's everywhere. And through the reductive part, if you do the sugar endoconversion game, you get a lot of glycolytic intermediates. So you don't have to actually burn them into energy. You can put them back into glycolysis and generate all the building blocks that glycolysis also generates, right? Phosphoglycerate, pyruvate, we've seen all these things. So an extremely important, as you will see, very versatile pathway, the pentose phosphate pathway, that is. So we're going to close at this point, and then we're going to see how it's regulated in the next video.